Partial differentiation can be very straightforward, but sometimes I will have compound functions and need to use the chain rule. Let's look at using the chain rule when I have one independent variable. There's a large number of real-world problems we might want to solve that will involve things that change depending on what happens to one or more of several factors. And those factors may in turn each depend on other factors as well. For example, a productivity model that's given by P is equal to the function f of LKR involves three independent variables, L, K, and R, that will each depend on other variables or conditions themselves. Changing a variable that L, K, or R depends on is also going to produce a change in P. The chain rule is what is going to give us the ability to work with problems like this one. So I want to review the chain rule real quickly. If I'm given y is equal to a function of u, where u is a function of t, then the derivative of my equation is given by dy dt is equal to dy du du dt. So now let's assume that I have z, which is a function of x and y are both functions of t. In this case, z depends on x and y, but x and y depend on t. So while z depends on x and depends on y, x depends on t and y does as well. The change in z with respect to x is the partial derivative given by dz dx, and the change in x with respect to t is the ordinary derivative dx dt. I use partial derivatives when the function I'm taking the derivative of depends on two variables, and I use ordinary derivatives when the function I'm taking the derivative of depends on only one variable. The change in z with respect to y is the partial derivative of z with respect to y, and the change in y with respect to t is the ordinary derivative dy dt. So if we have z, which is a differentiable function of x and y on its domain, and x and y are differentiable functions of t on some interval I, then my derivative of z with respect to t, dz dt, which is an ordinary derivative, is equal to the partial derivative of z with respect to x times the ordinary derivative of x with respect to t plus the partial derivative of z with respect to y times the ordinary derivative of y with respect to t. A function like z is equal to f of xt yt is a function where my dependent variable is z. The sole independent variable is t, and the variables x and y are called the intermediate variables. I have to go from z through x and y to get to t. The ordinary derivative dx dt and dy dt are used because x and y depend only on t. We have to use the partial derivatives, the partial of z with respect to x and the partial of z with respect to y, because z depends on both x and y. The derivative notation dz dt is used because ultimately z depends only on t once I've pulled the t up through the x and y functions. If I have a function z that's given by g of wxy, where wx and y are all functions of a single independent variable t, then I can simply expand my derivative to include that third term. dz dt becomes the partial of z with respect to w times dw dt plus the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. So let's work an example. I want to find dz dt when z is equal to x squared y minus xy cubed, and where x is equal to t squared and y is equal to t raised to the negative 2. Remember that I'm looking for dz dt is equal to the partial of z with respect to x dx dt plus the partial of z with respect to y dy dt. So I'm going to take the partial of z with respect to x, and I get 2xy minus y cubed. And dx dt is 2t. The partial of z with respect to y is x squared minus 3xy squared, and dy dt is negative 2 times t to the negative 3. dz dt now becomes the quantity 2xy minus y cubed times 2t plus the quantity x squared minus 3xy squared times negative 2t to the negative 3. Now I plug in t squared for x and t to the negative 2 for y. I get the quantity 2t squared times t to the negative 2 minus t to the negative 6 all times 2t plus the quantity t to the fourth minus 3t squared times t to the negative 4 all times negative 2t to the negative 3. I simplify what I can in the parentheses, and I get the quantity 2 minus t to the negative 6 times 2t plus the quantity t to the fourth minus 3t to the negative 2 times negative 2t to the negative 3. I go ahead and distribute the terms, and I get 4t minus 2t to the negative 5 minus 2t plus 6t to the negative 5, and this simplifies to 2t plus 6t to the negative 5. Let's work another example. I want to find dq dt when q is equal to the square root of x squared plus y squared plus z squared, and where x is sine t, y is cosine t, and z is cosine t. I have three variables, so I'm using the equation dq dt is equal to the partial of q with respect to x times dx dt plus the partial of q with respect to y dy dt plus the partial of q with respect to z dz dt. The partial of q with respect to x is given by x over the square root of x squared plus y squared plus z squared. dx dt is cosine t. The partial of q with respect to y is y over the square root of x squared plus y squared plus z squared, and dy dt is negative sine t. The partial of q with respect to z is z over the square root of x squared plus y squared plus z squared, and dz dt is negative sine t. I have to put that all together. dq dt is given by x over the square root of x squared plus y squared plus z squared times cosine t minus y over the square root of x squared plus y squared plus z squared times the sine of t minus z over the square root of x squared plus y squared plus z squared sine of t. I'm going to combine the last two terms, which are both products of sine, and I get x over the square root of x squared plus y squared plus z squared times cosine t minus the sum y plus z over the square root of x squared plus y squared plus z squared times sine of t. Now I'm going to plug in sine of t for x and cosine t for y and z. I get sine t cosine t over the square root of sine squared t plus cosine squared t plus cosine squared t minus 2 cosine t sine t over the square root of sine squared t plus cosine squared t plus cosine squared t. I'm going to simplify the denominator and combine the numerators, and I get negative cosine t sine t over the square root of 1 plus cosine squared t. So now you get to try it. Pause the video and find dw dt when w is equal to xy times the cosine of z, where x is equal to t squared, y is equal to 4t cubed, and z is equal to t plus 1. When you're ready, restart the video to check your understanding. I want to find dw dt, and w is a function with three independent variables. So I'm going to use dw dt is equal to the partial of w with respect to x dx dt plus the partial of w with respect to y dy dt plus the partial of w with respect to z dz dt. The partial of w with respect to x is y cosine z. dx dt is 2t. The partial of w with respect to y is x cosine z. dy dt is 12t squared. The partial of w with respect to z is negative xy sine z, and dz dt is equal to 1. This means dw dt is going to be equal to y cosine z times 2t plus x cosine z times 12t squared minus xy sine z times 1. Now I'm going to plug t squared in for x, 4t cubed in for y, and t plus 1 in for z. I get 8t to the fourth times cosine of t plus 1 plus 12t to the fourth times cosine of t plus 1 minus 4t to the fifth times sine of t plus 1. Combining the first two terms, I get 20t to the fourth times cosine of t plus 1 minus 4t to the fifth times sine of t plus 1. So identifying how many independent variables tells you which form of my derivative I need to use. And then I have to use the chain rule as I go through this. And once I have that all put together, I need to go back and substitute the t expressions I'm given for the x, y's, z's, or whatever independent variables I have. Let me know if you have any questions.